basic properties are the same. This function cannot be negative if we integrate it over the entire sample space. Here now, in two different sample space variables, then the integral should be 1. And if I integrate over just one direction, I get the marginal PDF in the other direction. So, this is where we stopped. And then what's interesting here, just like for the marginal PDF, also for the joint PDF, we can get any moment of any function of the sample space variables by just evaluating that function, multiplying with a PDF, and integrating over the entire sample space. And that's a very, very important property because you see immediately if I have the joint PDF of YF, YO, and temperature, if I have this joint PDF, then I can just evaluate this function here, integrate over the entire sample space, and I get the mean chemical source term. So that means that would be the closure problem would be solved by that. Okay, so here's an example just for a covariance. So this function could be this here, u1 minus u1 mean, u2 minus u2 mean. That's just u1 prime times u2 prime, and that gives me this covariance. So if I know the PDF, I can just compute this covariance, for example. Then another important concept is the conditioning, is the conditional PDFs. And so if I have a joint PDF, as function of v1 and v2, an interesting question could be, what is the PDF of v1 given a value of v2? Okay, so for example, if I have the PDF of temperature and mixture fraction, I could ask the question, what is the PDF of temperature given a mixture fraction that's equal to stoichiometric? Okay, given a mixture fraction of 0.055. Okay, because then I might get something that's very narrow, and I might get something that is close to the adiabatic flame temperature. Okay, so that is something that I can predict much more easily also than the PDF of temperature. I cannot predict the PDF of temperature, but the conditional PDF I might be able to predict. So that's a very important concept. So here, this shows the joint PDF of two variables, v1 and v2, and this is supposed to be a high value here, lower value, so little. You're looking at the so the value of the PDF comes out of the plane, and so then I could say, okay, I fix one value of v1, and then just if I go along this thing, I get this curve, and that just looks like now the PDF of v2. Okay, if I just evaluate this function for given value of v1, that gives me the PDF of v2. Is that right? Is that the PDF of v2? Or maybe not. Who thinks it's the PDF of v2? What I just said. Who thinks it's not the PDF of v2? Okay, and why? Any idea why? They are related to each other, but here I just picked this for this one value. It's right. If I just evaluate this here along this line, this is for a given value of v1, but this is not the PDF of v2 for a very concrete reason. Yeah, it's not normalized. Okay, who says the area under this curve is 1? As a matter of fact, if I would choose a different value of v1, maybe one that's down here, you see then this curve would go like this. I mean, it would have a smaller area. So you see immediately that this does not guarantee that the area is 1. So I take this curve, I evaluate its area, and I divide the whole thing by that area, and that gives me then a normalized PDF. So that's exactly what this is. So the conditional PDF, so we say here the PDF of V2 given, so the bar here means given U1 is equal to V1, given a certain value of V1, that's equal to the PDF evaluated at that point divided by this area, okay? And now if I integrate this, I can easily show that that is normalized, okay? So that's called the Bayes theorem because it relates the conditional PDF, the marginal PDF, and the joint PDF, okay? So, so that means from this then, I can also evaluate so-called conditional means, the mean of the temperature given that the mixture fraction is stoichiometric, okay, for example. And so I just use conditional PDF, evaluate this function, and this gives me the conditional mean, okay? This is the mean of this function given a certain value of V1. So now if U1 and U2 are statistically independent, then the conditioning has no effect, and then the conditional PDF is equal to the marginal PDF, okay? That's kind of obvious. And then Bayes' theorem here also says that if that's the case, V1 and V2 are independent, then the joint PDF is equal to the product of the marginal PDFs, okay? Only if these two are independent, then this is the case. That's an assumption that we sometimes make in modeling because these joint PDFs, very often in modeling, we need the joint PDF. And there are two ways to do this. So the joint PDF is equal to the marginal PDF times the conditional PDF. And conditional PDFs are sometimes easier to model. They are sometimes relatively easy to model. So that's one way to do it. Or the other one, if I can't do this, then the other thing, the other assumption that we sometimes make is we just assume the variables are independent and we evaluate the joint PDF from the product of the marginal PDFs. So so if these variables are independent, then the functions are uncorrelated. And the opposite is not always true. Something's uncorrelated doesn't mean the variables are independent. Okay, so that much for you know, just a little fresh up on these statistical methods. And we said if you know the PDF of the joint PDF of all scalars that we have, then the problem is solved. Then you can evaluate any correlations, you know, the mean of the source term and all of this. So the joint PDF of all scalars, you know, is something that solves the problem. And one idea to proceed would be to say, we just derive an equation for that function and solve that equation, okay? So that is called then the transported PDF model, or the PDF transport equation model, which was has been here proposed long time ago, but and different people have worked on this, but the person who really developed the technology to make that a tool that people now sometimes use in simulation is here Professor Pope from Cornell. And so this is the equation that describes the evolution of this PDF. And the equation is interesting because it has, first of all, it's an equation for this function, for this P function, the probability. And then what's interesting is that it has these derivatives here, not only in physical space, this is the derivative here in x, y, z, but it also has derivatives in the sample space here. So for example, here v, or here this the scalars, or here the scalars also. It has derivatives in physical space, but also in sample space. The other thing that's interesting is, which comes from that, the PDF of all scalars. Now think of how does that function look like? We said the PDF of a single quantity here, that's a scalar value. It's a scalar value because it gives you, it's a scalar value as a function of the sample space variable. Okay, so here's a one-dimensional function. And if you want to know this function in 3 dimensions in space, in every point, then it's a function of x, y, and z and the sample space variable. So it's a function in 4 dimensions. So you know, of course, that one-dimensional simulation is simple. Here, use this Flame Master code. It's fast, it's simple, everything easy. If you want to solve chemistry in 2 dimensions, that's a little more complicated already. If you want to solve things in 3 dimensions, that would be maybe a DNS or LES, that can be very, very costly. Here, we're talking about something that we want to solve in 4 dimensions, okay? Now, if you have a joint PDF of V1 and V2, now we're talking about 5 dimensions. You have to discretize this, essentially, in a 5-dimensional space, okay? So if you want to use, just to make that point, let's say you want to discretize this equation in one, you have x, y, z, and you want to have 100 points, grid points in each direction. It's 100 times 100 times 100, it's 10 to the 6, okay, is a million, right? So, so a million, but then here I have also as a function of V2, I want to have 100 points there, now it's 100 million, and then if I have two of these here, then a joint PDF of 2 variables, then I would say is 100 million, and then what is a billion, 10 billion or something, okay? So, and now comes the problem. We're not talking about a joint PDF of 2 variables. For a chemical mechanism, we have maybe 30 species plus the temperature. So we're talking about a 30-dimensional space, okay? You have to discretize in 30 dimensions. So that's one of the real challenges with this equation. It's an equation for a scalar. It's not even a vector. It's a scalar, but in a very high dimensional space. Okay. So so here you see the first 2 terms here are the local rate of change and the transport in physical space. These are terms that we know. These here are pressure and force, acceleration, and so on. And then this here is chemistry. Now, what's interesting about this equation, the way it is here, this is the joint PDF of not just all the scalars, which are here, but also the velocities, okay? Because velocities are also fluctuating function. And so this here gives you the joint probability of finding a certain combination of all the different scalars and velocities in 3 dimensions. That's the so-called joint velocity scalar PDF. And so this function here then is kind of a convection in velocity space. What this means is, let's say you have a pressure gradient and you accelerate the flow locally, then the probability shifts from low to high velocities. It just moves from low to high velocities. So that's what this term here does. And then this term here, that is now the chemical source term. And that is also just a shift in that space. If you have, let's say, you have cold before combustion, the probability is centered around low temperature. And once you get chemical reactions, then they shift the PDF to higher temperature or to higher product mass fraction. So this is what this term here does. And the nice thing about this is that these terms here now are in closed form, because here I know the PDF. That's what I solve for. I know the functional form of the chemical source term is just this here. And I can take the derivative of this. So this here is just sort the source term by dyf, by dyo, by temperature, and so on. All of this I can evaluate, and the source term is closed. Okay? So that is what sometimes what people say, that's the big advantage of this thing. This provides you the chemical source term in closed form. But then on the other side, this here is, let's not talk about here the velocity, because usually we're interested in scalar PDF. But this here is then the mixing term. This is transport. We said earlier, scalar dissipation is very important. We said fuel and air, they only react if they're mixed on a molecular level. And so this term here, that actually, you see this is a diffusion term, that actually represents or describes mixing on a molecular level. And the problem here is now, you see, this needs local gradients. This needs the local gradient of the mass fraction. But in this formulation, I don't have local gradients. I don't know what the local gradient is. I know the PDF of temperature here, and I know the PDF of temperature here. Okay? I know the PDF, the probability of finding a temperature at each point. But in order to evaluate the gradient, I need to know what's the value here, what's the value here, not the probability. Okay? So the probability can be the exact same on both points, but the gradients are very, very large or very small. Okay? So the gradients I don't know, so this term I can actually not evaluate. So catch-22, there's no free lunch. This method gives you this term now in closed form, but this term is unclosed. I have to provide closure somehow. Now we can already see for something that's mixing controlled, if the chemistry is relatively fast and is mixing controlled, then this is actually the most important term, and that is very hard to model. Okay, it's related to the scalar dissipation, but it's very hard to model. That's the biggest issue. So this was so one other thing that is very important is that if you have two terms, here in flames, we said you have molecular mixing somehow, and then the chemistry comes afterwards. And we saw earlier that actually if I just evaluate the chemical source term, and from this I evaluate a chemical timescale naively, we did this before, then we got a certain value for that timescale, and then we evaluated the timescale by considering the flame structure. And that was different, these two timescales were different by the Zeldovich number squared. So we said the Zeldovich number is about 10. So they were different by a factor of 100. So the chemical timescale is modified by mixing. Or in other words, if the chemistry is very fast and mixing is rate controlling, then these two, they are not independent. They're inherently coupled. You cannot decouple them. Okay? Or I can say it in different words, if I have two terms, and both are very, very, very large, and I take the difference, for example, then the difference between these two is much smaller than the values of each. And if I model these two independently, and I model one just a little, I have a little mistake in one, then the difference will be off by a large magnitude. Okay? So the point is that it is very dangerous to say this term is closed, I just evaluate it, and this one needs to be modeled in a totally different way because they're inherently coupled and they might have to be modeled together. So that's what was shown here also in an old paper here from the 80s, that in premix combustion where these processes are very strongly coupled, much more strongly even than in diffusion flames, it's difficult to model these terms. Now, the application, I said earlier, it is very hard to discretize a function in a 20-dimensional space. I mean, it's not possible. 3-dimensional space is very, very hard. 4-dimensional space, forget about it. So maybe 4-dimensional, but 5-dimensional, forget about it. Okay, so, people have developed techniques here that allow you to evaluate this. So the technique that is used is the so-called Monte Carlo simulation technique. So rather than discretizing this equation, it is written in a totally different form with a set of stochastic differential equations which are then solved for what's called notional particles. Or you could say, I just take millions of individual points that fly through the massless points that fly through the flow field, and they undergo all the reactions and they undergo all the chemistry, and each one is statistically a little different. And then at the end of the day, I can, from all these individual points, they're all like individual measurements, I can construct my PDF. And the nice thing about this is that you can imagine if you have a 30-dimensional space, not every point in that 30-dimensional space will be encountered in reality. I mean, as a matter of fact, only a very, very small subspace is typically accessed. So this Monte Carlo technique, it only gives you points that are realizable, that are possible. And so because of that, the computational effort doing this is much, much smaller. So these Monte Carlo technique, you use a large number of so-called notional particles, and then you solve these stochastic differential equations for these. The issue here is that the statistical convergence is relatively slow. It goes with the number of notional particles, with the square root of the number of notional particles. But so you need to have a lot of these particles. The application has been mostly for the joint scalar PDF without the velocities, but people have also looked at joint scalar and velocity PDF. Then the application is most often in steady thank you. So the application most often in steady RAND simulations. Steady RAND simulations, then the flow field is kind of steady, and you can just pass these particles through the steady flow field, and you can get you can do time averaging. So you don't need all that many particles. For simulations that are unsteady, you would need at every time in every cell a sufficient number of particles to make it statistically convergent. So let's say you need 500 particles per cell to get good statistics. That means if I have 1 million cells, I need to have 500 million of these particles. So that's a lot. And for each one of these, I need to solve a homogeneous reactor for the chemistry. And so the computation times are very, very high. But people figured out ways maybe to not use that many particles, less than these 500, and also people have figured out ways to make the integration of these homogeneous reactor equations cheaper, and so on. So there has been a lot of work in this area. So an example for an application in LES is shown here. In LES, then we don't call this the PDF, we call it the filtered density function. The filtered density function has is defined in a very similar way as the filtered quantity, I mean, in relation to the PDF, in a very similar way as the filtered quantity in LES. But it has different properties than the PDF. It doesn't have the same statistical properties. So that's something that one has to worry about a little bit. So that's what I just said. LES is unsteady, so one needs to have a large number of notional particles. And in LES also, one of the issues is that now you have these particles, but at the same time you need to evaluate the density, the mean density in a cell. So one always needs to interpolate, and the particles, they move with a velocity that's computed in a cell. So one always needs to interpolate back and forth between the particles and the Eulerian mesh. And so numerically that's difficult. Integration is expensive, and there's a technique here. In situ adaptive tabulation is a technique that also Professor Pope has developed, which makes this integration a lot faster. So let's see. So the simulation, we did a simulation here actually some years back. This was the first PDF simulation that was ever done in LES with a detailed description of the chemistry. And the only reason why we could do it at the time was NASA had a new computer, and somehow I can't remember, it was very hard to compile the code on that new machine. But this was, at the time, was one of the fastest computers in the world. It was at NASA Ames, I think. And so we had access to that machine, and here Venkat Raman, he worked with me at the time, and he managed to get our code to work. And so we were the only one using the machine. So he used this, at the time, whatever, fastest supercomputer in the world, just by himself, almost by himself, for a week or two, and then the simulation was done. So, but it was a very, very expensive simulation. Anyway, so this joint scalar PDF, and here we use only a few particles per cell, hope that that doesn't cause a problem. 19 species here in a mechanism. The mixing term I mentioned earlier, that's I don't talk here really about how the closure for this is being done, but there are models like here the so-called interaction by exchange with a mean model. That's a model that's very simple, that's often used, and all it says is that mixing always leads every single state to move a little bit more towards the mean on average, okay? So that's what it's called here, interaction by exchange with the mean. It has a time scale which is related to the scalar dissipation rate. The scalar dissipation is important, I said this earlier, and it has, here it evaluates the mean in each cell, and it just makes every particle moves every particle a little closer to the mean value. That's what mixing does. And then this is a simulation here of a jet flame, and you see the temperature here. This is low Reynolds number, this is higher Reynolds number, or let's say this is high Damköhler number, this is lower Damköhler number. And you see here that then you get local extinction here once in a while. This here is the scalar dissipation rate. You see you get these layers here of very high dissipation rate. And whenever you have this very high dissipation rate, like here, then you might get local extinction. Here, you might get local extinction. Here also local extinction, and so on. So high dissipation rates, they can lead here then to local extinction. And then if we look at the comparison here with data, this temperature, and for this flame D and flame E, or high Damköhler number, lower Damköhler number, then you see it's not so bad actually. You see this is oxygen, so this is as function of mixture fraction. These are conditional mean values. The symbols are the experiment, the lines are the simulation, and you see that the fuel here, the fuel should be on this side. The fuel actually has oxygen in this particular experiment. There's some oxygen in the fuel. The laser diagnostic people want to prevent the formation of PAHs, which would interfere with their lift measurements, and so they put some oxygen here in the fuel. But you see here, the oxygen for stoichiometric conditions, it should go to zero. It doesn't quite go to zero, and that is because finite rate chemistry effects. That is because the chemistry is not infinitely fast. And then here in this flame E, where you get more local extinction, you see that the oxygen mass fraction here is even higher, okay? Or here close to the nozzle is higher, a little downstream, it burns a little more. So the comparison with data is not so bad. Okay, so that's the PDF, the transported PDF model. Any questions about this?
So how do the costs compare to DNS?
Sorry?
How do the costs
compared to DNS? Well, it's very different. I mean, you should really ask your advisor because he's the expert on this. Here, Dr. Rahman, who has done these simulations. But you cannot really compare the two because the reason for the cost is very different. In DNS, you do one single homogeneous reactor calculation, let's say, in solving your chemistry in a splitting scheme per cell. But you have a huge number of cells. And here, you don't have that many cells, but in each cell, you have to solve many, many of these. So in DNS, you solve, of course, the transport which is also an important part of the computation cost. If you have 30 species, then you have to solve transport for these 30 species and the chemistry. So because the cost comes from very different issues, it's hard to compare. But at the time, that can be said, at the time, a DNS of this flame was not possible. Even now, a DNS of this flame is not possible. Maybe you see people doing DNS of this flame, but it's probably not right. I think the Reynolds number here is, if I remember this right, 24,000. And I said yesterday, maybe 15,000. That's something one can reach. But the Reynolds number here is too high for DNS.
So if you're doing DNS using finite rate chemistry, does that mean that you don't need a turbulence chemistry interaction model since you're basically solving?
Yes, that's exactly what it means. Because everything is resolved. There are no statistics, but there are no fluctuation below what you resolve. So the issue in modeling is that really, so this could look a little bit like DNS. So if but here locally we have value of temperature, but it really represents a fluctuating value at an even smaller scale. So these fluctuations I need to model. But in DNS, I would try to resolve every single fluctuation there is, and then there's nothing I need to model.
But using the same idea, would it be possible to come up with a grid size that is, still LES, it's still affordable, but then it's fine enough that you don't need a model after all? Is it possible?
No, it's not, because if you do LES, there's something on the subfilter scale, there's something happening. And if that is not very important, then maybe yes, that's what people call implicit LES. They just use a bad numerical scheme or a tailored numerical scheme that has enough dissipation to take this might work or not, It might work for one case, but not because it's tuned then for one case. It doesn't have physics. I mean, it just says whatever happens at the small scale is not important, and I just try to take it out without compromising on the larger scales. I don't know if this works or not. But for chemistry, it certainly doesn't work because that's what we said. All these small scale fluctuations, this is exactly what leads to the interaction. I mean, when we have local extinction here, these are small-scale processes which somehow need to be modeled. They happen on the subfilter scale. Yeah. So for some questions, that might be an option or not. I don't know. I'm not a big fan of things that are not based on physics. I like physics. I like things that are based on first principles somehow. I can understand the simplifications step by step, rigorous simplifications, and we can always go back and say, okay, we can test each assumption we make. And if you say, if people say, I just use the numerics, it's not based on first principles. And again, but maybe it still works for some cases where really large scale are only important, but for combustion, it certainly does not work. Okay, so then I want to show you a few other models here now specifically for premix combustion and models specifically for non-premix combustion. The point I just tried to make is that combustion happens at the small scales. And what happens at the small scales is the interaction of local transport and the chemistry. And when we talked about laminar flames, we saw that for premix and non-premix flames, this is very, very different. I mean, it's entirely different if I talk about a premix or a non-premix flame. And I think that if we now model a chemical source term, that's another thing I said earlier, we cannot just model the chemical source term just by itself. We always need to model the chemical source term somehow in connection with a small-scale transport that's going on. That's what I tried to show in the previous lectures. And that means that this interaction of small-scale interaction of transport and chemistry, that is very different for premix and non-premix combustion, or maybe for partially premix combustion or whatever you want. And I think one has to worry about these differences and do the model differently for premix combustion or for non-premix combustion, because that interaction is very different for both of these combustion modes. Which also means if there's something like partially premix combustion, I need to worry about that also. And so what we have done in the past is we have developed models for premix combustion, just premix combustion. We have developed models for just non-premix combustion. And then we have spent a lot of time actually to try to integrate these together so that we can do anything from premix to non-premix. But at each point, the model always worries about what contribution here comes from premix, what comes from non-premix, and how do I model this then on the small-scale interaction in a way that it represents the physics. So that's why I want to talk here first about models for premix combustion, not just our models, and then non-premix combustion. And I won't talk about how to put all of this together. But if you're interested, you can find this somewhere. So one of the really classical models, and I think also maybe even if we don't apply this model, it's very good to understand how turbulent premix combustion happens and what the issues are. One of the classical models is the so-called Bray-Moss-Libby model. Or BML model. And so this BML model, it starts out by defining a progress variable. Progress variable is just defined. Here we said this is premix combustion. Progress variable is defined to be 0 in the unburned and 1 in the burnt. Okay, that's it. So I can define it by using the temperature like this, or I can define it using a product mass fraction, CO2 mass fraction. Sometimes we define it by somehow a combination of CO2 or the main products and the intermediate products. So maybe just the sum of CO, hydrogen, CO2, and water. You can do whatever you like. If it has to be 1 in the burnt and 0 in the unburnt. So that's a progress variable. And you see, if I have a temperature equation or mass fraction equation here, I can because this here is a constant, I can very easily derive an equation here for this progress variable. And then we said, okay, if I have an equation for the progress variable, I can apply the averaging to this, here Favre averaging to this, and this is the equation I get. And you see there are two unclosed terms. Again, one is here this scalar flux term, and one is the turbulent flux term, and one is the chemical source term. Okay, so these two now we want to close, or we want to look at here in this limit of this Bray-Moss-Libby model. And the basic idea of this model is that we say this is a model now which is formulated for what we call the corrugated flamelet regime. In the corrugated flamelet regime, we said even the smallest turbulent scales, they are large compared to the entire thickness of the flame. which means the flame is undisturbed by the turbulence, and we can assume the flame, given a certain size of turbulence, we can assume the flame is infinitely thin. Okay, that's the assumption here. If the flame is infinitely thin, then in the burnt, Process variable is 1. In the unburnt, it is 0. And there's no other possible value of the Process variable. Okay? If the flame is infinitely thin, and I do millions of measurements, the probability that I find the value in the flame is 0, because it's infinitely thin. Okay? So any measurement I do just gives me a Process variable of 0 and 1. And so, so intermediate states are very unlikely. Okay? So we model now. So this means we can. Was there a question? No. We can immediately model or find a model for the PDF of Process variable. And we said earlier, well, if we have a problem that depends on a scalar, and I know the PDF of that scalar, then everything is done. I can close all terms. So the PDF of the Process variable then is a double delta function. Okay, because there are only two allowed values, 0 and 1, which means I have a delta function here at 0 and one delta function at 1. So the PDF of C is alpha here, which is the probability of finding unburnt, alpha times delta of C plus beta times delta of 1 minus C, and beta is just 1 minus alpha, okay? Because both of these together have to be equal to 1, okay, to satisfy a normalization condition. So this is the definition of the beta function, and we said this earlier already. So then this is how the PDF looks like. You see here, let's say this is a flame. Here's burnt, here's unburnt. And then if I look at a point, if I do measurement, let's say this is statistically stationary, which means I get fluctuations like this, but the mean flame front is always at that position. Let's say I do measurements here at this position, very far upstream of the flame, then I will only measure unburnt mixture, a Process variable of 0, which means I have only one delta function here, and the strength of this is equal to 1, so alpha is equal to 1. If I measure very close to the mean flame, but still on the unburnt side, then I'll find a double delta function where this here is a little stronger than this. Alpha is larger than 0.5, let's say. If I'm exactly at the mean flame position, finding burned and unburned condition is equal. Each one of these is 0.5. And then I'm far in the burned, then the probability of finding burned is larger than unburned. Okay, so that's how this looks like. I think it's not so difficult. So now we want to look at first how we close the turbulent transport term. Now the problem with the turbulent transport term is, of course, it does not only depend on the Process variable, it depends on the Process variable and the velocity. Both are fluctuating quantity, and so I need the joint PDF. If I want to model this, I need the joint PDF of velocity and Process variable. Okay, so that is shown here, the joint PDF of velocity and Process variable. And so I take this scalar flux here. Q is now the scalar flux. I put this in here, and then I should write it like this. So the Q here in this case then would be U minus U mean times C minus C mean. Okay, that is, this should be the Favre average. So this would be U prime prime, and this is C prime prime. And if I plug these in here, I know this PDF, then I can evaluate this. Okay. So let's look at the PDF. The joint PDF of U and C. I can write this as the marginal PDF of C times the conditional PDF of U given a value of C. Okay? That's what we saw earlier. That's just Bayes' theorem. And that is nice because of two reasons, really. The PDF of C, I know already. There's only one parameter that I don't know. This is alpha. but it's, you know, it's only a function of alpha, but I know the shape of this function, okay? That's great. How about this PDF here? Can I say something about this PDF? This is the PDF of u given c, and the only possible values of c are 0 and 1, which means this is the mean velocity in the unburned, on the unburned side, or it's the mean velocity on the burned side, okay? So if we have a flame here, let's say, and we have a turbulent flow that comes in here, then locally here I get a mean velocity, and this here just says, okay, take the average just on this side, that gives me u unburned mean, let's say, and then take the average just on this side, gives me u burned mean. And these are things that I can actually model much more easily than the mean velocity, because basically what we know is the velocity comes in here, and here it must be 7 times as large, let's say, because of the expansion. So, so if I do this, then I can plug in the this PDF up here, and I can here the Q I can plug in, and I can just evaluate this. So first of all, just the PDF here is here PDF of C, which was alpha times delta of C, and then the conditional PDF here, this would just be F of U, or the PDF of U in the unburned and PDF of U in the burned. Okay, but I get these two different parts to this, and this now I can this here is exactly what I said here. I can plug this in, and I can evaluate this. There's some algebra here which is skipped here. You can try this at home, but what you get at the end is that this function here, this scalar flux, is equal to c times 1 minus c times u burned minus u unburned. So u burned, that's what I had here, is just the mean velocity in the unburned, the mean velocity in the burned. Okay? So that's interesting, because now just by making this assumption that the flame is thin, it gives me a model for the scalar flux without really any further assumption. Okay? I still need to somehow evaluate these, because I solve a momentum equation which gives me the mean velocity, but it only gives me the unconditional mean. So I somehow need to figure out what are the unconditional, what are the conditional values given the unconditional values. But that's doable. Okay, so that is so here we didn't need to make the assumption of a gradient transport assumption, which we usually do. You know, we just get it from the assumption the flame is thin. And now this is interesting. So you burned. Let's look at a flame like this. This is supposed to be a turbulent flame. This is unburned. This is burned. Here's the velocity, the conditional velocity in the unburned, conditional velocity in the burned. And as I said, the burned velocity, because of the expansion, is larger than the unburned velocity. Okay? So the burned velocity is larger than the unburned velocity. So this difference here of the velocity is larger than 0. Okay? Then, so this here is the model for the scalar flux. This here is larger than 0. The Procus variable is always between 0 and 1. So c times 1 minus c also is always larger than 0. So this thing here, by this model, is always larger or equal to 0. Okay? Now, let's see what would have happened if we had used a gradient transport assumption for the flux. Gradient transport assumption says minus diffusivity times the gradient. In this case, the gradient is larger than 0, okay? It's positive. dt is always positive, but it has negative sign. So this here is always negative. It means the flux goes from here to here, okay? The flux goes from the burned to the unburned. But this here shows us the flux actually, it goes the other way. Isn't that interesting? I mean, everyone and their brother use the gradient transport assumption, even for premix combustion. But this shows maybe it's not a good idea. There's a process here, as well known, it's called counter-gradient diffusion. Actually, this term here, which is supposed to be a turbulent diffusion, it actually goes from cold to hot. Why is that? Because of the expansion. You have two effects coming together. You have the turbulent transport that goes from burnt to unburnt, and then you have the expansion, which actually pushes things in the other direction. And so if you just evaluate this term, you get what's called counter-gradient diffusion, okay? And for stronger turbulence, that's for weak turbulence, that is a very important effect. If the turbulence gets stronger, then the gradient diffusion, it becomes stronger again, but is an effect that the effect of the heat release is not to be neglected here. Okay, so that's, I think, is a very interesting result that the simple model shows us, where we only made one single assumption, really, that the flame is infinitely thin. Okay, so now if we want to do the same thing for the chemical source term, I could say, let's evaluate the chemical source term with the PDF. Actually, the chemical source term for C equal to 0 and C equal to 1 is 0, or for C equal to 0, it's almost 0. And that means if we would do that, the chemical source term would be 0. So that wouldn't work. That assumption that there's no state between 0 and 1, that doesn't help us close the source term. So here we use a different way. We use what's called a flame surface density model, and which is shown here. So we just say, that's what we said last time, the mass burning rate of a flame like this, it's just the unburned density times the laminar flame speed times the area, okay? And the sigma, so this is per unit volume. So this here is the flame area per unit volume, okay? So we call this the flame surface density. And then locally, another thing we said, locally the burning velocity is not the unstretched, it's not the same as the unstretched burning velocity. It's modified by local strain and curvature and so on. And so this I factor here is the strain factor, or the stretch factor, which considers local increase or decrease actually of the laminar burning velocity. Okay, so this is a model that one can use. Now I still need to know the sigma, and for sigma there are algebraic models like this, which relies on a length scale. So this is an algebraic model, or there are transport equation models like this. So this here is a kind of an empiric, is similar to the epsilon equation in a sense that it just has these convective transport here, a turbulent transport, and then it just has a production term here, which is proportional to epsilon over k, and it has a dissipation term which is proportional here to sigma squared. And what's interesting about this is that this here also, it is the limit of fast chemistry. It doesn't know very much, this model. It doesn't know anything about the chemistry. There is an SL here, but you see that if I would multiply the entire equation here by SL, it would give me an equation for SL times sigma, okay, as one variable. If I multiply this by SL, then here I have SL times sigma. Let's call this F, and then here I have SL times sigma F, and this is F squared. So I can solve this equation for F without knowing the value of SL, okay? And then here you see SL times sigma, again, is just F that's appearing here. Then I can also evaluate this source term without knowing the value of SL, okay? So this equation here actually, if I use this in combination with this model, it's independent of SL. It's for, you could say, it's for infinitely fast chemistry. Okay, then the next step here would be do a different model here is the level set model. That's a model that we already introduced. You know, we talked about laminar flames, and we formulated this for an instantaneous flame front without talking about averaging. And so that's a method that we have spent, that we in our group have spent a lot of time with developing over the past years, is also available in commercial codes, and it's very often used for example, for doing simulation in internal combustion engines. This here, basically, the next few slides, they just show what we did already. We started out with a point on the flame surface and said it moves around with a background velocity, and then also by burning normal to itself. So that is a point that is on the flame surface. Then we said we define a level set function. We take the substantial derivative, set it equal to 0, and then we replace this by the equation I just showed, and then we get this level set equation. And by also defining a normal vector here based on the level set function. So that's what we said that's what we derived yesterday, I think. And so that just describes the dynamics of this flame front that propagates normal to itself. This was now derived for a thin flame. Basically, we just said this is where the flame is. So in a sense, it was also derived for an infinitely thin flame. And so you could say the way we derived this also is for the limit of the corrugated flame regime. And the question then is, what do we do for the thin reaction zones regime, which is technically actually more important because it's the higher level of turbulence limit. And so that's, so this here, let me just finish this up, and then we will have a break. So in this regime then, we said this equation just describes the evolution of this front. Then in the unburned and in the burnt, we need to somehow define the function differently. That's done here by defining this as a distance function. So the gradient is 0 everywhere, means every point just describes the distance from this function. Then for the burning velocity here, we can use the burning velocity here modified by stretch, meaning by curvature and by strain. And this also we discussed this week. And if I plug this in, I get this equation here, which describes the evolution of the front by a burning velocity, which is impacted here by strain and curvature. Okay, so that let's stop here, and then in the next lecture we'll talk about how to extend that for the thin reaction zones regime.